rates of change and the derivative. Our objectives in this lesson is to find the average and instantaneous rates of change and velocity of a function, find and use the derivative of a function at a number, and find an equation of a tangent line and a normal line. This picture might look familiar, where we explored the slope of the secant line and the slope of the tangent line. Let's begin with the slope of the secant line. Another way to say that is the average rate of change of a function over an interval from x to c. So our secant line, this green line, is showing 2 points where the line intersects the function y equals f of x, this blue curve. Point P is at an x value that we're going to call c. And the other point on the secant line is at another x value we're going to call x. And of course, the slope of any line, which often we signify with the letter m, is the change in y over the change in x, or the second y value minus the first y value over the second x value minus the first x value, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Now, when we label our x values c and x, and our function is called f of x, that rate of change is the y value at x, f of x, minus the y value at c, f of c, over the change in x, x minus c, the difference between those x values. Now notice, as we go from a picture of this secant line where the x values are this far apart, we bring the x values a little bit closer together. So here's the x value, c and the other x value. And the next picture, we've brought those two x values even closer together. So notice what's happening. This x value is getting closer to that c value. The change between them is closer and closer together, or there's less of a change. Finally, that c value is the same as that x value. And because the line touches at only one point on the curve, it's now called a tangent line. The slope of the tangent line is called the instantaneous rate of change because it is the rate of change of the function at one point. Another name for that is the derivative. So we call it the slope of the tangent line, the instantaneous rate of change, or the derivative of f of x at one point, x equals c. So notice the relationship when it's the average rate of change, f of x minus f of c over x minus c, simply the slope formula. And when it's the instantaneous rate of change, or the derivative, where it's the limit as x approaches c, because those 2 points are becoming the same point of that slope formula. And this is the notation for the derivative. F prime of c is how that's said. In quotes, we can write how we say that. F prime of c is that limit as x approaches c of that rate of change. Now, the velocity of a function is an application of the rate of change. Velocity is the rate of change of the position function. Let the signed distance s will be representing a distance from the origin at time t of an object in rectilinear motion along a line, be given by the function s equals f of t, where t moves over a time period of t equals a to t equals b for a not equal to b. The average velocity, and of course that means over an interval, is this average rate of change, the change in y, in this case the change in position, over the change in time. The instantaneous velocity means the rate of change at one point. And that's going to be denoted as s prime of t, the derivative of the position, which of course is the limit as the points in time get closer to each other to become like the tangent line and the 1 point of tangency of that average rate of change. Let's take a look at some examples. Find the derivative of the function f of x equals the square root of 2x at x equals 8. So we remember that the derivative, f prime of c, the derivative at a point, is the limit as x approaches c of the rate of change, f of x minus f of c over x minus c. In our problem, this is f of x, that radical function, and this is c, x equals 8. So let's rewrite what we have. F prime of 8 equals the limit as x approaches 8. Our f of x is square root of 2x minus f of c is square root of 2 times 8, and that's divided by x minus 8. Now we can simplify a little bit. The limit as x approaches 8 of square root of 2x minus square root of 16, which is 4, over x minus 8. Now, of course, when we're evaluating limits, we begin by trying substitution. Can we plug 8 into here and it works out just fine? We cannot. Unfortunately, we get 0 in the denominator. So what's another strategy that we try when we have radicals? That's right, multiplying by the conjugate. So I'm going to multiply the numerator by square root of 2x plus 4, and therefore I need to multiply the denominator by the same square root of 2x plus 4. Let's see what that gives us. The limit as x approaches 8. When I distribute this, I get 2x. The outers and the inners make 0, and negative 4 times 4 makes negative 16. In the denominator, I have x minus 8 times the quantity square root of 2x plus 4. Now I notice my numerator factors, so I can make that the limit as x approaches 8 of 2 times x minus 8 over x minus 8 times the quantity square root of 2x plus 4. And I see I have a common factor that divides out. And now that I'm able to divide that out, I can do my substitution. Let's plug in the 8 where we see the x and see what we get now. 2 over square root of 2 times 8 plus 4. That gives us 2 over square root of 16 is 4. And then 4 plus 4 is 8. And we can simplify that to 1/4. This is our derivative of the function at that point x equals 8. Two, use the function f of x equals x squared plus 3 and the point on the function negative 1, 4 to do the following. A, find the slope of the tangent line to the graph of the function at the indicated point. Well, of course, slope of the tangent line, we recall, means the derivative, f prime of c. And of course, f prime of c, we write as the limit as x approaches c of f of x minus f of c over x minus c. Let's apply this to our problem. Our x value is negative 1, so that's the c we're plugging into our function x squared plus 3. So we'll write that the slope of our tangent line is f prime of negative 1, which is the limit as x approaches negative 1 of f of x, which is x squared plus 3, minus f of c, which is our c plugged in to the function, negative 1 squared plus 3, divided by x minus negative 1. Let's simplify this expression and see what we have. The limit as x approaches negative 1 of x squared plus 3. Negative 1 squared is 1. 1 plus 3 is 4, so we're subtracting 4. Or better yet, we can write this as x squared minus 1 divided by x minus a negative 1 is plus 1. Now, of course, substitution yields 0 in the denominator, so can we do something to manipulate this function? And yes, we can. The numerator can be factored. So we'll rewrite limit as x approaches negative 1, x minus 1 times x plus 1 over x plus 1. And now we have a common factor to divide out. And then, of course, we can use our substitution and plug the negative 1 in for the x. So negative 1 minus 1, which makes negative 2. There is the slope of our tangent line. Part B. Find an equation of the tangent line to the graph of the function f at the indicated point. Well, an equation of a line can be written in a variety of ways. I prefer the point slope form of the equation of a line, which is y minus the y-coordinate, we'll call it y sub 1, equals the slope m times x minus the x-coordinate, we'll call it x sub 1. So given the slope, which is negative 2, and the point, which we're using x sub 1 and y sub 1, is that indicated point, negative 1 comma 4, we'll plug in what we have. Y minus the y-coordinate is 4 equals the slope, negative 2, times x minus the x-coordinate of negative 1. We could stop there, but of course it's easy enough to pretty this up and write it a little bit simpler. Y minus 4 equals negative 2 times x plus 1. This can be written in all sorts of ways, but this is an equation of the tangent line, and we're good to go. C. Find an equation of the normal line to the graph of the function f at the indicated point. Normal means perpendicular. Lines that are perpendicular have slopes that are opposite reciprocals. So the slope of the normal line is equal to the opposite reciprocal, or negative 1 over the slope of the tangent line. Therefore, the slope of our normal line is equal to negative 1 divided by negative 2, or positive 1/2. Then we go back to our point slope form and write the equation. Of course, our indicated point is the same, so we have y minus the y-coordinate 4 equals our new slope 1/2 times x minus the x-coordinate of negative 1, or x plus 1. And there's an equation of our normal line. Three, find the rate of change of this function at part A, c equals 2. Notice that we're finding the rate of change at 1 point. This is 1 point only. What is the rate of change at 1 point only? That would be the derivative, or in this case, f prime at 2. f prime at 2 is going to be the limit as x approaches 2 of our function x squared minus 5x minus our function with the x value 2 plugged in. So 2 squared minus 5 times 2 over x minus 2. Let's see how that looks simplified. The limit as x approaches 2 of x squared minus 5x. 2 squared is 4. 4 minus 10 makes negative 6. And I'm subtracting negative 6, so that would be plus 6 over x minus 2. Now, of course, substitution yields 0 in the denominator, so let's see if I can manipulate. It looks like my numerator can be factored, so the limit as x approaches 2, the numerator will turn in to x minus 2 times x minus 3 over x minus 2, and now I have a common factor, and I can use substitution. 2 into the x, 2 minus 3 gives me negative 1, and negative 1 is my rate of change at the point c equals 2. How about the rate of change of the function at any real number c? Well, in this case, it's still at one point, so it's still the derivative, but it's the derivative at any c value. Let's see how that looks different. The limit as x approaches c of our function x squared minus 5x minus our function with c plugged in, c squared minus 5c over x minus c. If we get rid of the parentheses, that would give us limit as x approaches c of x squared minus 5x minus c squared plus 5c over x minus c. Now, of course, we try substitution, but c minus c would yield 0 in the denominator. So how can we rewrite this? Well, it might not be obvious at first, but if we do some rearranging, we'll be able to factor and find some common factors. So let's look at how to rearrange. The limit as x approaches c, I'm going to put the x squared minus the c squared together. You'll see why here shortly. X squared minus c squared, and then minus 5x and plus 5c. Minus 5x plus 5c, still over x minus c. Now I did that because x squared minus c squared is a difference of squares, and that can be factored. Limit as x approaches c, x minus c times x plus c is our difference of squares. And then this group can be factored by taking out the common factor negative 5. And I'm left with x minus c. Notice that I have a common factor in each of these groups of x minus c, and now that can be factored out. So I'm going to rewrite limit as x approaches c, taking out that common factor of x minus c leaves me with this factor, x plus c, and this factor of negative 5 over the denominator x minus c. Now you'll see why I did that. I've got a common factor that divides out. And now I can do the substitution, c going in for x, and get c plus c minus 5 or 2c minus 5. And there is my rate of change of the function at any real number c.